Hey everyone, I hope you had a great Easter weekend. Welcome back to statistics here. We're going to be continuing on with our discussion of confidence intervals. We had talked a little bit last week about computing confidence intervals for proportions, and this week we're going to do the same thing, except we're going to be doing it with means. Okay, so averages, means, instead of proportions and percentages and things like that. Okay. So our task today is to estimate the mean mass of all M&Ms at 90% confidence. Okay, so again, notice here, this time what we're estimating is a mean and not a proportion. So some things are going to be the same, some things are going to be different. So you're going to want to follow along with these notes and kind of make note of those things that are different between the proportion and the mean when it comes to confidence intervals. Okay. Also, try and think back when we were in class and we did an experiment with M&Ms in class where we had weighed the M&Ms and we used it to build a distribution and a histogram, and we also created a frequency table and all that other stuff. So we're gonna be reaching from that data for today's notes. Okay. So let's think about what's going on. Just like with the confidence interval for proportions, we're going to be relying on a sampling distribution, but instead of a sampling distribution for the proportions, we're going to be looking at the sampling distribution for the means. Okay, so this is where that central limit theorem pops up again that we talked about 2 weeks ago. Okay. So just real quick review of the sampling distribution for the means. We saw that when we take repeated samples of data, the sample means have a shape that resembles the shape of the original population, with the effect that they normalize as those samples are increased. Okay, so the larger the sample size, the more normal the sampling distribution is going to be. And typically, once that sample size was 30 or more, it was safe to assume that the sampling distribution was approximately normal. So if we took repeated samples of size 30 or more, we would end up with a distribution of means that was normally distributed. Okay, the center of that normal distribution was the mean itself, right? So the mean of the sampling distribution was equal to the mean of the population. Okay, so that center did not change, but the spread did, right? So as the sample size increased, we saw the spread decrease. We saw that standard deviation get smaller, and we could actually calculate the standard deviation of the sampling distribution by taking the population standard deviation and dividing by the square root of the sample size. Okay, and this is kind of where things get a little bit difficult to go with, okay, because we have a problem, right? If you think about what our task is to estimate the mean mass of all M&Ms, and to calculate the spread, we actually need to know what the mean mass of all M&Ms is, right? We need to know the population mean and the population standard deviation to calculate the standard deviation of the sampling distribution. Well, we would never estimate something that we already know. So we don't know this piece of information. We don't know what the mean of the population is. That's what we're estimating, and that means we don't know what the standard deviation of the population is. So we really can't calculate this. So what statisticians have done for a very long time is they've said, well, you know what, that standard deviation that we get from our sample that we take, that's close enough. We're just going to substitute that in for the population standard deviation, and we'll use that. All right, so that's where this information in the box is coming from. This is what we're talking about here, is when we make that replacement for the population standard deviation with the sample standard deviation. It's considered sloppy, all right? And it's not perfect. It doesn't perfectly estimate. And a long time ago, there was a guy named William Gossett, and he worked for the Guinness Brewing Company, and he figured out how to accommodate, or not accommodate, but how to handle the difference between using these two things. All right, so there's a discrepancy between those, and he was able to create a new kind of distribution known as the student's t distribution, which took into account the difference between the parameter and the statistic here. Okay, so this sloppy version of the normal distribution is what we call the student's t distribution. Interesting fact, the reason that it was called the student's t-distribution is because William Gossett, when he wrote his paper on the t-distribution, he submitted it as anonymous. Essentially, he called himself the anonymous student, because if he had used his name, the Guinness Brewing Company would have claimed ownership of his paper, and the rest of the mathematical community would not have been able to have used this. So he submitted it under the name Anonymous Student, which is why it's called the Student's T-distribution. Okay. So the other really cool thing about the T-distribution is that it's actually not just one distribution. It's a collection of many different distributions. And he noticed that as the sample size changed, so did the shape of this curve, right? And like I said, these are all different normal distributions, and you can see the different colors here. They kind of correspond with this box over here. So you'll see like the blue curve right here in this distribution. That's one of the curves in the T distribution. And this DF with the 2 over here, that is corresponding to a sample size of 3. So this thing, degrees of freedom, is always 1 less than the sample size. So this is showing you what the normal curve would look like if we took repeated samplings of 3. And then if we wanted to see 4, we would look at the red curve. And then if we wanted to see 8 degrees of freedom, we would look at this orange curve right here. So you see like the curve changes based on that sample size. And this is what William Gossett figured out, is he could actually predict the shape of every single curve based on every single sample size that you could possibly take. So he was able to account for the differences in those curves, and thus the differences in the areas underneath the curve. Okay, so each of these curves looks pretty normal, but it is still slightly different. But because he took into account those differences, his confidence intervals were much more accurate than just using the normal distribution like statisticians had before him. Okay, the degrees of freedom thing, as far as understanding like why did they do the degrees of freedom, there's a good explanation in the textbook. You are more than welcome to read it, but for an introductory stats class, it's not necessary for you to understand the theoretical side of the degrees of freedom. But I would read the excerpt from your textbook closely, and if you're interested in why the degrees of freedom works the way it does, I would recommend an advanced statistics course to continue your studies. For an introductory, we're just trying to get you using this in an application sense and understanding what's going on in a broad sense. Okay, so don't worry too much about that. Just remember, the thing you need to know about degrees of freedom is that it is 1 less than the sample size. Okay, all right. So enough of that. Right. So again, just the takeaway from this is we have to use a t-distribution because of this right here. We don't know the population standard deviation. We're making a replacement with the sample standard deviation, which causes all kinds of different curves to appear, and we will select the right one when we get there. Okay. So to start our confidence interval, we actually need to gather data. So think back before this whole coronavirus thing came in, we were in class, we measured M&Ms on the scale, we weighed them, and you gave me all of your data, and we got this, right? So this was our original spreadsheet that we built together as a class, and we got a mean, and we got a standard deviation here. Okay, so I'm gonna go record those in my notes, right? So you have to pretend that you actually just weighed a bunch of M&Ms, and this is what we found. We found the mean of our sample to be 2.339, and we found the standard deviation of our sample to be 0.36, and our sample size was 660. So I'm gonna jot that down. And these are really the 3 important things that we need from the data that we gathered. Okay. So we want to summarize the data, and we want to do this based on its shape, its center, and its spread. This is where most things in statistics begins. All right. So when we talk about its shape, all right, we still want our sample sizes to be 30 or more, even though the specific reason Gossett created the t-distribution was to be able to handle very small sample sizes as small as 2 or 3. The statistical community still relies on those sample sizes being greater than 30. Ours was 660, so our sample size was much greater than 30, so we know the shape is going to be normal at this point, right? Remember, this is the shape of the sampling distribution. So I'm just going to draw that here. And this normal curve that I'm drawing is one of these sloppy curves from the t-distribution. Okay, now our center, right? So remember that our center is the same as the population mean. So whatever we find from our sample, which was this 2.339, that is going to be our center. So we got our center of this distribution occurring at 2.339, and this is what we call our point estimate. All right, this is the middle of our confidence interval. All right, the spread, okay, so remember the spread gets smaller as the sample size gets bigger, so we can take our sample standard deviation here, this 0.36, and we are going to divide it by the square root of our sample size. Now recall, normally this should be a population standard deviation, not the one from our sample, but we are making that substitution, which is forcing us to use this t-distribution instead. You'll see where that comes in later on. Okay, so this is a sloppy calculation of the spread. So we're going to get 0.014 here. That's going to be the standard error that we use. Remember, this is what we call our standard error. Right, and this is our point estimate. Okay, so we've summarized our data based on the sampling distribution, and now we're going to start building our confidence interval here. Okay, so just a quick recap. Remember, the recipe for a confidence interval is we take our point estimate and then we add or subtract the margin of error. The margin of error is calculated by taking the critical value based on the confidence level and multiplying it by the standard deviation of the statistic in repeated sampling. Okay, so let's go through each of the major components that we need to build our confidence interval, and let's make sure that we have them and know where they come from. Okay, so our point estimate, that was our sample mean. We calculated that on the front page. That was going to be 2.339 grams. All right, so our average from our sample was 2.339 grams for the M&Ms. Okay, the standard error, right? So we calculated that by taking 0.36 and dividing by the square root of 660, which gave us a 0.014. So this is what we're going to use for our standard error. And remember, we don't know the population standard deviation here. If we did, we would use that here instead of this 0.36. Okay. Our confidence level, I'm going to skip over here because the next thing we're going to do is the critical value. But our confidence level, remember we stated at the beginning, we wanted to do this with a 90% confidence. So they usually give that to you in the problem. You just have to read carefully for what that confidence level is. Okay, so that means that we want to encompass 90% of our distribution. So we need to know how much area is in the tails, right? So this alpha represents the complement of the confidence level. So in our case, it'll be 0.1. Then to figure out what our alpha over 2 is going to be, we take 0.1 and we divide it by 2, and we get a 0.05. That is the percentage of the distribution that will be in each tail. Okay? And we need that because we need it for calculating our critical value. Okay? So notice that things have changed here a little bit. Instead of a z, we have a t. That's because we're using the t-distribution, and we know that we're using the t-distribution because we substituted in the sample standard deviation here instead of the population. So that forces us into this t-distribution thing. Okay, so instead of doing an inverse norm, right, so this would usually be an inverse norm to calculate the critical value, we're going to be using an inverse t distribution. Okay, and the inverse t, and I'll show you here on the calculator in just a minute, uses the area to the left in one of the tails. So we'll put that 0.05 here, and then the degrees of freedom is what we need for the second parameter for that. And that is going to be the sample size minus 1. Okay, so I'm going to go over here. We're going to be doing an inverse t. And we're going to be putting in a 0.05 for the area to the left. And then our degrees of freedom, remember our sample size was 660. So our degrees of freedom is 659. And this will get us our critical value for this distribution. And so let me pull up my calculator here and we'll calculate that together. Okay. We're going to go on, and I'm going to go second vars, and you'll see inverse t is option number 4 here. I'm going to hit enter. I'm going to tell it again, the area in that tail is 0.05. The degrees of freedom is 659. And we're going to paste and enter. And something happened. What did I do? I had an extra parenthesis in there. Okay, so let's go second. Oops. Let's do a second enter. And I'll get rid of that parenthesis. There we go. And enter. There we go. So we got 1.647, right? So remember, you do get a plus or a minus. So you get plus or minus 1.647 here. So those are our critical values. And again, to kind of explain what that means, you have to remember our distribution. Right, here's our distribution. We want to capture 90% of that distribution because we're doing a 90% confidence interval. So that 0.05 is here. And then these values are the T alpha over 2s. Okay, these are the boundaries that kind of cut off those 5% tails that we're looking at in the distribution, right? So we have 0.9 here and then 0.05 on each end. And you have to remember, this is not a normal curve anymore. It's one of the T distribution curves. That's why we're doing the inverse T instead of an inverse norm. Okay. Now, once we have our T alpha over 2, we can actually plug that into our margin of error calculations. We had our standard error, which is 0.014, and then we multiply that by our critical value, 1.647. And let's get that calculation real quick. So we got 0.014 times 1.647. And we got a margin of error of 0.023 grams. And so it looks like I've got all of the major pieces that I need. Let's see if we can actually put together our confidence interval at this point. Okay. So remember, our recipe, right, was point estimate plus or minus the margin of error. So our point estimate was 2.39. Plus or minus our margin of error, which we calculated by taking our critical value and our standard error, right? So we took our critical value of 1.647 and multiplying it by 0.014, and we got 2.339 plus or minus 0.023 grams. Okay, so we have expressed our confidence interval here in the plus or minus format. And now we're going to express it in the other two formats. So if I actually take 2.339 plus 0.023, I'll get 2.36. A little bit of rounding there. And then if I do 2.339 minus 0.023, we'll get 2.32 if I were to round the 2 decimal places there. And then the last format here is what we call the interval format or open interval format. And we would just put in those left and right bounds. So we'd say 2.32 and 2.36, right? So these are our 3 formats for a confidence interval, right? You might see any 3 of these in the MyOpenMath homework. Okay. Last thing we need to do is interpret. So we're going to say, I am 90% confident that the mean mass of all M&Ms is in between 2.32 and 2.36 grams. Okay. So that's a by hand confidence interval for the mean. Again, just some key things to remember. We made that substitution because we did not know the population standard deviation that forced us into using that student t distribution that was invented by William Gossett. If we did know the population standard deviation, we would just use a normal distribution like normal, right? No pun intended there. So the last thing I'm going to show you is how to do this on your calculator, because you can, all that by hand stuff we did, you can do it with the calculator. Your calculator knows all about confidence intervals with means. So let me show you where that's at. If you go to stat, you go over to tests, you're going to go down here to where it says t interval and z interval. So if we don't know the population standard deviation, you want to use the t interval because we'll be using the t distribution. If you do know the population standard deviation, you would use option 7, which is the interval that's going to use the normal distribution. So for our experiment that we just did, we used a t interval or a t distribution, so we're going to use the t interval option here. If we were in class, I would let you use this option where we would just take the M&M data that we recorded, we'd put it right into list 1, and then we could calculate our confidence interval straight from the data, but we don't have that, so we're going to use the stats option here. So we have the stats, right, where we calculated the mean of 2.339, and then our standard deviation that we got from our data was 0.36. Okay. Don't put the standard error in, put the standard deviation from the raw data. Okay. Our sample size was 660, and our confidence level was 0.9. And then we'll calculate and see if we got the same thing that we did by hand. And we did a little bit more precise, right? We got the 2.32. If we had rounded here to 2 decimal places, that's what we would have gotten. And same thing here with the 2.36. So we can get that interval right away from the calculator and check our work. All right, guys, that's good for day 1. Make sure you check back in, watch video 2. We'll talk about some of the more finer details of this stuff in the next video. All right, guys, have a good day.